All right. Yeah, you should be able to see my screen. Yeah, so 2D geometries in CENOS induction heating. So what exactly does that mean? What that means is that we can take geometries such as the ones on the left, which would be quite complex in 3D cases. So this would be some kind of a bearing, this would be some kind of a shaft, hardening. This is something also quite interesting. And these would take quite a long time to produce and set up in 3D, as well as require difficult CAD for the inductors and so on. But what we can do, if they're axially symmetric, is simplify them in objects which look kind of like this. So as you can see, they already look a million times easier and oh yeah, more easier to set up. Yeah, why should we even use the 2D geometry approach? So the calculation times are like it's even tough to compare how much more quicker they are. They can be run as well on less powerful systems, and of course, since the system and the whole case is a lot smaller, our mesh can be a lot finer, and that leads to increased accuracy. Then some of the cons of this approach, one of them is that it can be only used for 100% axially symmetric geometries, and the setup time as of right now is a little bit longer than FromCAD 3D approach due to the old workflow and the manual meshing that we have to do. All right, without further ado, we can jump in the in CENOS main menu, and we can start with the way how such case can be set up, how to also get some 2D files out of your 3D kind of CAD files and so on. So as I said, so the first thing which we will do, we will get our 2D CAD files out of a 3D kind of CAD files. So to do that, the first thing which you need to do is just open the Advanced Geometry Editor. Here we can already select the CAD files which we would like to use. So I have prepared some previously. And they should be here on the, just a moment. Yeah, so this one. Open it in there, press open the editor, and yeah, also save the case just so it has some kind of a name for it. In this case, we will not use, we will just use it to get the 2D files out of our 3D step files. Give it a moment to open, and we will proceed in just a moment. So yeah, some of you might have even not seen a Salome interface before. So this is actually where we'll be also working in a moment. But the main thing which is interesting for us right now is on the left. Here our geometry menu can be opened, and we can see that imported geometry file which I mentioned just previously. Here, if I press the eye icon, and the icon here which zooms into the geometry, we can see the CAD file which I have chosen. For me, so it's one of the CAD files which I presented in the presentation. So here's the workpiece. Here's one inductor, like one inductor winding, second inductor winding, third, fourth, and yeah, this is what we will use. One thing to mention always when you kind of want to position your CAD files in order to export the 2D faces, always have these faces exactly on the XY plane. That's something which has to be correct. Yeah, to get these faces out, so what we can do, we can click on this imported geometry, so that will be your 3D file. Press over here on the top the button explode, and we can explode this solid into faces. To do that, we choose the type here to be faces, and we press select subshape so that we can select which of the faces we actually want to get out. If I zoom in here, so the first one which it actually wants to give me is the air. So that's the larger face right over here. I click on it, press apply, and here on the left we can see that the air face has already been taken out. Now what I can do, I can click on it once again, press hide, yeah, actually press it another time, and then we can see the like also the workpiece and the inductor spaces. In a similar way, we click on the workpiece, press apply. Here we go the workpiece space, and in the same way for each of the inductors. Oops, I actually hide it. Just a moment. Hide it again and select it. Apply, and the same way for each of them. After you get these spaces out, so that's all that we need. We can like check if it's all that we needed. Yeah, so the air is fine, the workpiece is okay. And to get these faces out, what we need to do is just like scroll over all of them and just go here to File, Export, and we can export them as step. And these will very nicely be able to use in the 2D simulation. Yeah, so press here and just select wherever you would like to have them. For me, I will just have them on the desktop, and since I have multiple, I will actually, you'll be able to see how many of, how these multiple faces actually get saved. So yeah, just click save a couple of times, and each of them will be saved. Yeah, so that's it for at least getting 2D files out of your 3D geometry. I won't be going in the cutting process and the movement, but that can also be done with the shaper section and the rotational buttons over here. Yeah. All right, what we can do now is go back to the CENOS main menu, press make a new case. Right now we go once again for the advanced geometry editor. And now what we'll do, we'll save the case. In this case, like in this time, this will be the actual case that we will be using. So we can write in, let's say, CENOS webinar 1, let's say. Press enter, and here where we press choose CAD files, we will now choose our faces. Click on it, go to the desktop, and for me, so it's phase 1, phase 2, and phase 3, phase 4, phase 5, and phase 6. Press open, and right now we can click on open editor, and all of these phases should be waiting for us there. Okay. Yes, so Salome has opened, and right now in similar way as we used to do it. So here on the left, we open the geometry dropdown, and we can see all of our files which we have imported. Once again, click the zoom button, and we can see how our files look like. They are perfectly aligned with the XY plane, so everything should be perfect. Now the overview of what we will be doing in Salome. The first thing which we'll do, we'll put all of this in a partition to have it in a single geometrical file. Then we will make the groups, so which one is the inductor, which is the workpiece, and so on. And then we will also move on to the meshing section to split all of this geometry up into triangles, for which we can then send it back to CENOS and do the calculations. To put all of this in a partition, we just scroll over all of our files here and go up here to the button called partition, click on it, and here you can see already our objects have been chosen, and the only thing to keep in mind that the resulting type here should be face. So click that and press apply and close, and right now all of our geometrical objects are in a single group. So here you can see that they are in this partition. Now, as I mentioned, we will be making the groups for each of these geometrical objects. To do that, right-click on the partition, go above to the button Create Group, And here's where all of the magic will happen. On the top, we have to select what exactly we want to, what kind of group we would like to make. So we can select either the faces, which is also needed for, which will be needed for the 2D faces which we have, and also the lines which will be needed for the workpiece interface, similarly as you would have in 3D simulations, as well as workpiece symmetry, in this case air symmetry and air infinity. All right, then let's start with the faces. So click on the faces button, write the name for the first group which we would assign. Let's say the workpiece, write it in, and here very nicely just click on the workpiece, press the button add, and press apply. And on the left, you can see that the workpiece group has already been made. In a similar way, we can go with the air group. So write in air and click here on the air face. Press add and apply. And then the last groups which we need to have is the inductors windings. For these, you can rename them. I will just leave the name as group 1, group 2, and so on. So just click on the winding, press add, apply. Once again, click on the next winding, press add, apply. The third one, add, apply, and the last one. Now on the left, you can see that all of our phase groups have been already made. If you would have also flux concentrators, you would make a phase for that. If you would have multiple workpieces, you would also make, of course, a separate group for that. Now what we'll be taking a look at are the line groups. So here, if I press on the lines, we can see all of the lines. As I said, so the one which we'll start with will be the workpiece interface. So right in workpiece interface, and yeah, if we zoom in, we can just click on all of the face on all of the lines which are inside of the air domain. So this one, hold down Shift and select all of the ones which are inside of the system. As I mentioned previously, the one which is on the symmetry axis will be put in a different group. As you can see, I have selected all of these lines by hand, but if your workpiece would be a bit more like difficult, let's say with more lines, one useful filter to use here is only subshapes of the second shape, which in our case would mean only lines of a certain face that would appear. And we can also try to use it if I click here and select my workpiece face right over here. We can see that only the lines of a certain workpiece have appeared. So right now it's very easy. We just press select all, and all of them are taken into our group. Of course, as I mentioned previously, we do not need this line right now. So click on that one and remove it. Press apply, and then we can move on to the next group, which is workpiece symmetry. Same, just as easy as it was for workpiece interface, even easier. Just click on it and press add. Now for the next line groups, let me just re-enable it. For the next line groups, we will need to have the air symmetry. So this is this line and the line on the top here. So that will be air symmetry. Press add, apply. And then also air infinity, which are all of these ends of the airbox, which are like outer ends of our system. Yeah, press add and apply. Yeah, and that's pretty much all of the line groups already made. One thing which I can mention, if you would have a case where your workpiece is further away from the axis, so it's not sitting on top of the axis, you actually would not have the workpiece symmetry group. You would just have all of the lines as workpiece interface. But yeah, but this is the minimum of groups that we need to further set up the simulation. All right, now we are ready to go to the meshing section, since all of our small groups are made. Line groups are made for the physics, so that's all good. To go to the meshing, we can press the button up here, And what we will proceed with is splitting all of our geometrical objects, so the workpiece, inductors, also air, into triangles, so that the electromagnetic calculations afterwards have an easier time of doing all the calculations. Because as we know, for a triangle, we can pretty much calculate anything which we want to. So that's why we need to simplify our geometry into these triangles. To create the mesh, what we need to do is click on the partition. So this will be our large mesh, which contains all of the other data which we were like making right now. So click on the partition, go above to the button create mesh. And right now what we need to do is click here assign set of hypotheses, and through the automatic triangulation, which means pretty much through the automatic splitting into triangles. Then you will be presented with a max size value. What this means is like it's asking for the maximum size of the triangles which should be like made for this mesh one. So the size is like the edges of the triangle. So the smaller it is, the smaller the triangles will be. For the mesh one, it's okay to leave this value as it is, but of course for the smaller submeshes, we will need to use smaller triangles because they're not as large as the whole system and the airbox. So press OK, and one thing which I can personally recommend that you do is change the algorithm from Triangle Mephisto over to NetGen 2D. That will just result in a bit more of element count economy, which will result in faster calculations in the end. Press apply and close. And right here on the left, our mesh one has developed. Now we will go through the reason why we need to make the submeshes for each of the separate groups. I can represent that visually if I try to compute this mesh. If I compute it, so here for some reason there's no errors, but if we zoom in, so if we remember how our system did look like, so now we pretty much cannot understand where our workpiece is and where our inductors are. So that's why we need smaller triangles for the smaller objects which are in our system. But okay, then what I will do, I will click on mesh one, right click and clear the mesh data so that this mesh which we have doesn't just sit here when we will make the new submeshes. To make the submeshes, we click on mesh one, go above to the button create submesh, and then from the partition we choose for which face we want to make that submesh. I would say let's start with the workpiece. So I click on it. I also love to rename the submesh in its name. And then once again, we go to assign set of hypotheses to the automatic triangulation. And right now, as I said previously, so we have to reduce this max size value to something smaller. So here it's 0.03, that's in meters. So let's go with 0.005. Let's see what happens. And then we will understand if it's perhaps the triangles are too small or it's okay. We will have a look. Pressing OK. And then, yeah, here I can once again suggest that you change the algorithm from Triangle Mephisto over to NetGen 2D, as well as choose here at the gear icon the option length from edges. Once again, these two things are not obligatory, but they they might help for some more complex geometries to not have that much problems. All right, apply and close. And here on the left, we can see that the submesh has developed. I will right click on it and try to compute it, and we'll see what happens. Yeah, so submesh has computed without errors. And if we zoom in, we can at least right now see at least the workpiece geometry and how it looks like. For a 3D case, maybe this would be perhaps all right to run with the mesh this course, but for like 2D case, I would for sure want to make it even finer because then again, the simulation will still be very quick. And if we want to see better heat distribution on the workpiece, then of course we need to have these triangles smaller. the temperature distribution in the end, like precise temperature distribution, will only be as good as your mesh is fine, pretty much. At least that's something to keep in mind. So to change that max size value, we can go to mesh 1 first, just clear the mesh data, make sure there's no leftovers, then go to our workpiece, right click, edit the submesh, and now we need to go to the 1D section, where we have our max size value, and we can either edit it with this button, just edit this value which we have here, or click on the gear icon and make a whole new max size. So that's what I will do. Here we can see our max size was 0.005. I will try it with a value of 0.001. So that's 5 times smaller, but I hope it won't be too crazy. Yeah, apply and close, and now we can once again right click on the workpiece and try to compute it. Okay. Yeah, so you can see mesh computation has succeeded. And if we zoom in, so the workpiece is a lot more fine. Right now you can see the triangles are very, very tiny. So in reality, I would make it perhaps a little bit coarser, but for this example, it will be perfectly okay. Yeah, then in the same way, we will proceed with the inductor submesh. So for the inductor, once again, click on mesh 1, right click, create submesh. And right now we actually need to take all of these 4 groups together because it will be just easier for us to mesh, because the same max size will be applied for all of these objects. So to do that, I hold my mouse button and scroll over all 4 of these objects to select multiple of them at the same time. I will write in its name to be inductors, but in reality it would be probably windings. But yeah, I just write in its name, assign set of hypotheses to the automatic. And right now I will input the max size value. I will actually go 2 times coarser than the workpiece. So that would be 0.002. One quick tip which I can tell you, which we have seen, if you are interested more in the workpiece heating, you can go quite rough with the inductors mesh. The results shouldn't change too much, even if your inductor is quite a bit rougher than the workpiece. Once again, of course, we select the algorithm to be again 2D and hypothesis to be length from edges. Yeah, press apply and close, clearing up the mesh data once again, and computing the mesh. Okay. Yeah, so the mesh has computed. So right now what it does is it computes all of our submeshes and the large mesh as well. Here I can close it, and we can see how the large mesh triangles look like. And then as we move in closer to our system, the mesh is a lot finer since we implemented those submeshes. Yeah, right now at this point we are almost ready to send everything back to CENOS. So yeah, but there's still one thing which we have not yet dealt with, which is also necessary for induction heating simulations, and that is the skin effect. So to take into account the skin effect, we need to actually make kind of like a smaller, maybe even thinner mesh objects on the very surface of the workpiece. So depending on your frequency, the material you're running, we get the correct current density, and the current gets soaked up nicely into the workpiece. To perhaps put it in more visual terms, I can show you here on our documentation page what we'll be doing. So here it is explained. So the skin layer, here we can see the mesh, which we can see right now, and here are those very thin elements on the surface to make sure that our current density is fully absorbed into the workpiece. Yeah, right now we will also be going through this creating viscous layers option. Yeah, so to create the viscous layers, we need to go to the workpiece, right click, edit the submesh. And here in the 2D section where we have add hypothesis, we need to click on the gear icon and click on the viscous layers 2D. Here you can see three values which we have to assign. The total thickness, which as I said depends on your frequency and the material you're running. Number of layers, so that's how many of these viscous layers we'll have. Generally, to put it simply, the higher the frequency, the more layers are recommended. And the stretch factor, by how much each of the next layers will be larger, like multiplied by a number larger than the previous layer. The stretch factor usually is just as one at 1.5. Number of layers for the workpiece is usually never lower than 4. If possible, then you can also have 5 or 6, or for high frequencies even like 8. And the thickness value, that is a good question. How do we get the thickness value? To get the thickness value, we have developed a small viscous layers calculator, which will also be shared with you after the meeting. And this viscous layers calculator right up here, how it functions is that you input the magnetic permeability of the workpiece. Here you can see some common values, which is a good approximation for different steels. The frequency which you would be running, and the maximum electroconductivity of your steel or the material which you would be heating up. So here, let's say we will be running 42 chromium molybdenum for steel, so magnetic permeability is 1. Frequency, let's say let's run it with 10 kilohertz, so that will be 10,000. And on the right, you will be it will be already possible to see how these values change once I press enter. So yeah, so you can see the values changed a little bit in this case, but the frequency didn't change that much. But if it's high frequency, these values will change a lot. The electric conductivity, this can be seen on in our material library, but here we have also like placed a couple of more common electric conductivity values. So for 42 chromium molybdenum for steel, here is the value to use. Just copy it and put it here. And right now, these values should be a pretty good estimate to have a good current density absorption into the workpiece. Yeah, and here on the right, you can also, like, if you want to have more layers, it just readjusts that value. But since we are going with 4 layers, so here I check the value which I have here meters, so 0.0037, and I just go back to the meshing section and write it in, so 0.0037. Once again, this value is an approximation. It's probably okay if you run it with 0.004 or 45, but still, it's best to consult with that calculator what kind of value, at least roughly, to input. You can press OK, apply and close. Once again, clear the mesh data and recompute the workpiece so that we can see how the viscous layers actually look like. Yeah, so here mesh computation has succeeded. We can close it up. And if we zoom in, we can see how these viscous layers look like. So in this case, I think they're actually the geometry is a bit too thin to have our recommended viscous layers, because here you can see that the mesh is kind of like is being pressed together. But in such cases, when your geometry is actually thinner than the viscous layers actually would like to be, you can just go back to the viscous layers and reduce that value a little bit. So here we have our viscous layers, and if our total thickness was 0.003, we can go with 0.0028, let's say 28. And it shouldn't like impact the results, just to make sure that we don't have some kind of mesh collisions or something like that. Yeah, okay, now these parts look a lot better. In the same way, we will be making these viscous layers for the inductor. If I click on the inductor, right click, edit submesh, we're going for the viscous layers. And once again, number of layers, I will have as 4, stretch factor 1.5, and the total thickness, we just go to the calculator and check here for the copper. So this is the inductor part, that the value is 0.0009. So we just take it 0.0009. Press OK, applying close, and we can right now clear the mesh data and just compute the entire mesh. Okay, so right now mesh has computed. You can see also the number of elements, which is 9,000. Some of you who have dealt with 3D simulations probably know that in 3D simulations, the lowest amount usually is like 50, 100,000, 50 or 100,000, and usually it's closer to 300,000. So you can already imagine how much more faster this simulation can be. Yeah, if I close it up, here you can see the viscous layers both on the workpiece and on the inductors. At this point, the mesh is ready to be exported back to CENOS. Yeah, so to export it out, we click on Mesh 1, Tools, Plugins, and send the mesh back to CENOS. Right now, all of the phase groups and line groups which we can see here are from are the same groups which we made in the partition. So we pretty much need all of them. The only one which we don't need is this auto group for inductors, which was made when we were making that mesh together for all 4 of the windings. Press send mesh to CENOS, and mesh is waiting. And in a moment, CENOS main menu will appear. Yeah, at this point, the meshing part has already been done. One thing to mention before we go in the physics, we can click here on the gear icon to make sure that the correct length units of geometry have been chosen. In this case, it should be the meters. Yeah, and now we are ready to jump in the physics and see some of the small differences which we have in 2D cases compared to 3D cases. All right, so yeah, as we enter physics, we can see that the window here on the left looks a bit different than usual, and on the right, yeah, the inputs are pretty much similar to how we have in 3D cases. So here we have the simulation control panel where more or less all of the general things are assigned, and then we have a separate tab for each of our elements. In this case, it's the faces. So going through the simulation control panel for axial symmetry, of course, in this case, we select yes, since the whole geometry is axially symmetric to the y-axis. For the time here, we input the frequency. The one which I inputted in the calculator was 10 kilohertz. So that's the one which I will use. 10 kilohertz. The end time depends on how long you want to heat it up. I would say let's go with 5 seconds, and you can split it up into the calculation time steps. Let's say if we would go with 0.1 seconds, so these 5 seconds would be split into smaller parts of 0.1 second. But something which I can advise that you do is actually use the adaptive time step if there's no motion in your case, because that will make sure that the case converges, that there's no calculation errors, and it will slowly make this very small time step into a larger and larger and larger time step when the magnetic forces start to equalize and the software understands that it's capable of making the time step larger. Yeah, about computation algorithm and advanced computation settings, nothing really to change there. I would say leave it as automatic and everything should be okay. Now for the motion, in this case, we will not use it, but I can also very quickly show you how that works. In the motion tab, we can click on it, create new motion. Remember that complex motion can be used in all cases, there's no limitations to it. So that's usually the one to pick, unless you know that your case can run on simple motion. And here you just select which of the domains you would like to move. So either our windings or our workpiece, and just input the velocity. Yeah, then moving on to each of our like separate domains which we have here. As you can see, we have group 2, group 1, group 4, group 3. So these are all of our inductors windings. In my case, I would like to apply the same current for all of them. So I will group all of them together by using that checkbox on the top right. Yeah, so just click on all 4 of them. If you would have more of them, let's say 10 or 50, that's also possible. And you can just click the group button, and all of them, as you can see, are in a single group right now. Next thing that we have to do is change the role here for the inductor. Of course, that should be the inductor. Materials copper. If you want to change it, you can click the X button and change it to aluminum, perhaps. Choose the like power or current or voltage you would like to run. I will run it with current, let's say 3000 amps, just to see what will happen. Or actually, no, five would be a better number, I think. And then yeah, that's pretty much it for the inductor. For the workpiece, so here for the workpiece, we have to choose the role. Of course, that should be the workpiece. And here we select the material. As I said, in this case, I would like to use 42 chromium molten 4. So I just write 42, press here on alloy steel, 42 chromium molten 4, and nothing really else to change there. Below here, we can see the initial conditions. This would change your starting temperature of your workpiece. So let's say if you have it preheated, you can change this value to, let's say, 200 degrees, and your workpiece then at the very beginning will be hotter than ambient air temperature. About the boundary conditions. So here we have workpiece interface and workpiece symmetry. Let's start with workpiece symmetry. So for this one, we actually have to select for the thermal analysis for it to be adiabatic. So this means zero incoming and outgoing heat flux condition at the surface, which just allows the simulation to understand that that is the symmetry axis. And well, yeah, so that we don't have some kind of a weird hole in our system. And here for the electromagnetics, workpiece symmetry, very convenient. We can just select the symmetry axis and nothing else to do with the workpiece symmetry. The other things, so for the workpiece interface, it's exactly the same as it would be in 3D cases. So we click here the option to open it, and we select the combined. We select always both convection and radiation. The emissivity value, that depends solely on the material. For 42 chromium molten 4, as well as some low carbon, medium carbon steels, we use emissivity of 0.7 or 0.8. In this case, yeah, let's write 0.8. So yeah, that depends solely on the material. The other property, though, heat transfer coefficient, this can change depending on if your part is in room temperature or is being actively cooled. If your part is in room temperature, this value is as low as 10. If your part, let's say, is moving at a high speed, there's some wind coming at it, this value can increase to 100, perhaps 200. And then when you start some kind of quenching, it can increase to 1,000, 5,000, and so on. In this case, I won't be running any kind of quenching, but if you want to, you can also have the quenching input as a table. So let's say for the first let's say 5 seconds, you would have a low kind of heat transfer coefficient, and then after the 5th second, you can input some kind of larger heat transfer coefficient to make sure that yeah, that the cooling is being taken into account. One thing which I can mention here, always make sure that you have both the both the start and the end time for each like change in the values. Okay, yeah, and below here, once again, workpiece interface, that is just selected as the interface. Then the last group to assign here, we have the air. So here we choose the role to be air. Material is air. Yeah, workpiece interface is already like chosen because it's inside of this air. And then for air symmetry, in a similar way, we just select symmetry axis. And for air infinity, very convenient, we go with the option infinity. As you can see on the top, our case is ready to be run. So this is pretty much the entire 2D case setup done. Yeah, thank you for being with me. Perhaps there's any questions or anything perhaps I could discuss.
I have a question. Max Wissing from Protec. The heat transfer, is it possible to simulate heat transfer from different materials, not only into air? Like from one steel into aluminum?
Yeah, that's also possible. What you would need to do then, since it's not a full CFD simulation that we're dealing with here, you would need the one like workpiece solid to be touching the other workpiece solid, and then this, let's say, if I would have let's say an additional block here, which would be directly connected to this face right over here. We don't need to assign anything then for that line, which is like the border line for them. The heat will just flow from one solid to the other.
So there's no additional line definition needed.
Yeah, exactly. You don't even need to like make an additional line group.
That's great.
Anything else, perhaps? Okay. Yeah. If oh, there is a question. Yeah. Jerome. Chat box. Oh, just a moment. Since capable of simulating induction heat of carbon fiber composites, specifically anisotropic properties. That's a good question. We have it. We have written about it in the documentation page. For example, using anisotropic properties for lamination for the flux concentrators. About the heating of carbon fiber composites, it sounds like I at least think that's also something which we could do, but I would have to consult with my colleagues on how specifically to approach that. But yeah, I can also send over that documentation page article, or I can get in touch with you after the meeting. No worries. Okay. Yeah, perhaps any questions about the meshing part? Oh, else? Yeah. Have you compared a 2D simulation with a 3D simulation of the same workpiece and inductor? I actually personally have compared 3D slice geometry with a 2D case setup. And I understand the question is probably what's the difference between them. And the difference in the temperature in the end is pretty much negligible. For the case which I set up, the only the temperatures were exactly the same. The only thing which might have altered them, like I don't know, 1 or 2 or 3 degrees, might be just perhaps the mesh was rougher in the 3D case than in the 2D case. But if you apply, if you have a full 3D case, or you have a slice geometry and you apply the slice here, in case of a slice 3D geometry, the results should be quite close. The only thing which can change, I expect, is here of course we imagine that the inductor is 100% around the workpiece, but of course in real life there might be some kind of a place where you have the terminals coming out, or some kind of like change in direction. There might be a slight deviation because of that, but it's nothing worth mentioning, I think, at least in most cases. Okay, I will go with the chat box questions, and then perhaps the other ones which are raising hands. Um, What about induction heat of lamination on different steel carbon alloy in 3D geometry, using multiple configurations of laminations? That would be for the induction heat of lamination. Um, you would mean that you want to perhaps use the lamination not for the flux concentrators, but to actually heat up that lamination material. Flux concentrators, yeah, for that we can also input the anisotropic properties. That's once again on the documentation page. I can check if I can find it. Physics. Um, yeah, it's somewhere here. I actually won't be able to find it right now, but that's also something which can be found, or I might be able to find it. Oh yeah, actually here in the field expressions option. In the documentation page, you can see more about the anisotropy or, well, yeah, some kind of ways how to actually apply it. Also, the carbon fiber, which was just mentioned, is also written here how that can be done. Um, yeah, I will just yeah, go by the chat box about the question which Wissing has asked, is there a list online with all the materials that's already set up in CENOS platform? I'm not sure if we have it, but if you also download the software, you can also check that. I can open the material library, and all of the materials here on the left are the ones which are predefined. So here's like alloy steels, aluminum, different grades for carbon steels, copper, of course, also different grades for flux concentrators, high carbon steel, Inconel, iron, and then different grades for low carbon steels, also stainless, and so on. So yeah, best way to check that is to download the free trial. Um, how do you count anisotropic skin depth effect? That's actually a good question. I have not really tried that, but I would think it's how the anisotropy happens in CENOS. So if you want to have laminations, that you would have like the geometry as a single block, and then with that expression which I showed in the documentation page, you would set it up in a way that, but yeah, as if it was lamination. So still that geometry block and the mesh for it will be still the same as we would usually have. At least that's what I would think. But I can ask the scientific department because that sounds like a bit of a yeah, a bit of a specific example. Um, yeah, I see. I have missed one question from Jerome about copper coil being typically hollow for coolant. Do we need to model the water inside? The response there is that in Salome, in the case when the inductor would be hollow, just a moment. Yeah, so if our inductor is hollow, all that we would have to do is add those the hollow parts inside to the air domain. So the air would have also not only the large block of air, but also the phases which are inside of the inductors. And then, if you want to go even further and simulate also the inductors heating, then you would have to make also inductor interface group. So both for the outer side of the inductor and the inner side of the inductor. And then in the physics, similarly as for the workpiece, you can just apply the heat transfer coefficient. So of course, a lot larger for the inside of the inductor and a smaller one for the outside, I would imagine. And also here in the physics, you would go to the inductor, change its role here, and also enable the thermal analysis. Okay, about the questions. Okay, I think that's okay. Yeah, there's another question. Yeah, that's true. We think we should also like write like input the available materials in our documentation page. That's something which I will also get in touch with someone who can change that. Yeah, about the raised hands, Raduku. Or is there? I cannot follow the raised hands. Is there anyone who would like to ask a question? Okay, I'm sure. Jerome, is it a raised hand or? Okay, got it. Yes, so yeah, if there's no other questions, then that's pretty much it from my side. Always remember, if you're simulating something and if you have any questions, make sure to use the support live chat here on the bottom right to get instantaneous response in case your case is not working or you have any questions. Yeah, all right then. Then that concludes the webinar. If there's no more questions, thank you all for being here. I hope you gained something insightful and will be able to use this also in your case. All right, see ya.